Okay, our next presenter is Steve Legansky. Steve is the founder and general manager of Intelligent Light, and you may know Intelligent Light from its main product, FieldView Software. Steve has a BE and MS from Stevens Institute of Technology. Steve is going to talk on HPC and bicycle wheels, which I know thrills me, the combination of the two, so I'm looking forward to hearing about that. Let's welcome Steve to our podium.
Thank you.
Let me just put my schedule here.
That should be okay. Sure. Well, good morning, everybody. First of all, I'd like to thank the HPCC for inviting me to present to you today. I was thrilled to get the invitation, and then I kind of freaked out because originally I was going to speak Wednesday. And we're a very small company, and this is the last week of our fiscal year. So between like doing contract things up in the room and reporting and budgeting, I was succeeded in getting my talk moved to today. So I'm very appreciative of that because I'm going to have to bail out tomorrow and sign some purchase orders or something. They tell me there's work for me at the office, so I'll have to head back down to New Jersey. So today I'm going to kind of tell the mishmash story of HPC, data management for CFD, and racing bike wheels, and hopefully by the end it'll make sense why those three things are on the one topic slide. I'll talk a little bit about Intelligent Light, who we are. As was mentioned earlier, we make the FieldView CFD post-processing software. A little bit about CFD workflows. CFD is the consummate big data source for computer-aided engineering. In engineering, as far as analysis is concerned, nothing else comes close. The story of Zip Bike Wheels, a company we've been collaborating with to bring high-performance, high-accuracy CFD to a true missing middle company. It's a great story. And then some of my personal comments on the missing middle, since everyone is really commenting on that and trying to find a solution to that. I've got a slightly different view, having worked with some companies in that area. So our company was founded in 1984. We've been in the software business for nearly 3 decades. Yes, I am that old. I predate frame buffers. Definitely. It's visualization for me started with line plotters. We launched FieldView in 1990 as a joint project with United Technologies and Pratt & Whitney. It's grown to have a global customer base. We have between 3,000 and 4,000 active licenses of FieldView out there, which makes us one of the largest players in CFD. We really focus on providing solutions to CFD. However, we don't do what all the other CFD companies do, which is deal with meshing and deal with solvers. We deal with everything else. So it's an interesting space to fill. We have CFD people on staff, and those people are one of the things that led us to working in the missing middle with Zip. Our mission as a company is to help our customers using CFD to do more with less and make better decisions. And the part about making better decisions, in my opinion, is one of the key points of being able to convince missing middle people to actually trust HPC-based CAE analysis. There are 3 parts to our company. FieldView software products, they're comprehensive in scope from a laptop to HPC. We have customers in Japan, for example, Sumitomo Rubber Industries makes Dunlop golf balls, doing 3 billion cell unsteady calculations to optimize the dimples on a golf ball. They're a little bit bigger than a missing middle company, but 3 billion cells per time step is pretty big in the world of CFD. We also have products for data management. We have a toolkit called XDB Advantage, which lets data be compressed on the cloud and brought down and used in a more efficient form, and also tools for advanced automation, because we're big believers in batch processing using HPC as much as possible. We either sell the products directly or other companies such as Altair, which is one of the biggest companies in automotive CAE, resell our products. We have a services team that helps people automate, helps people get a good workflow going. We'll talk a little bit about that later. And then an applied research group, which is really focused on research such as SBIR-funded projects. And those projects feed into FieldView. We only take projects that are strategic in nature. We're just finishing one for the Air Force with a brand new automated feature detection technology for unsteady CFD technical stuff. We just were awarded one yesterday by the Air Force for reduced order methods. And all of these things are really focused on data management. They're fancy words for it. But when Dr. Goh showed his slide in the morning of big data at one end and a small binary decision on the other end, our job is to get to that decision as quickly as possible. So what about CFD workflows? What's up with that? There it is. So now thank you very much for your time today, and I'll be moving on. In a nutshell, CFD is small data in, big data out. I mean, literally, you can put in something on the order of 1 megabyte of input data and generate terabytes of output data. And of course, that doesn't work very well in a remote computing kind of environment, because it's really easy to get yourself in trouble. You can submit a lot of small jobs and end up with way too much data to bring back. And that's certainly a problem for American industry. Certainly one of the largest companies in industry have told us that they can only look at 10% of what they can calculate. So this is my diagram of the CFD workflow, and to get technical here, I've put a little plot in the background showing data size as you go through the workflow. So you start up with some simple idea, like that windshield wiper example that Addison gave us in the morning. I think I can change the shape of that windshield wiper and make it better. And that's where all the trouble begins, right? You just want to know at the end, is it better or not? Well, I got to take some CAD, I got to build a mesh, I got to make an input deck, run it through a solver, get on my HPC resource, generate terabytes of data, run it through some post-processing software so I can either look at it or analyze it, and then at the end come up with my answer. And everybody in the field of CFD is consumed with all this middle stuff. That's what their practice is about. That's what their jobs are about. But for the engineer, those are not the important things. He wants an answer as quick as possible, as minimum amount of work. So in the typical workflow, you've got some big bottlenecks, like reading or copying large results files takes a long time. You have to send gigabytes over the internet, doesn't work. We're big proponents of FedExNet at Intelligent Light for many of our customers still today. And if engineer is waiting to read, he's not engineering, he's waiting to read. It seems trivial, but I would imagine lots of money gets wasted in the U.S. every day reading files. So those are the kind of problems we like to attack. Repetitive analysis. If to go to the windshield wiper example today, where HPC would benefit that guy is, I want to evaluate 120 windshield wiper designs. So now I got to rent 120 cars and send them all around the world. Then the scale becomes an issue. That's where HPC can really provide you the benefit. But the problem for the engineer is that if he's doing this manually, he's just going through and clicking all these buttons over and over again, trying to figure out, or my favorite is making lots of plots and putting them on the wall and attempting to learn from these plots on the wall. Interesting balance problem. Although desktop systems have become more powerful, HPC's gotten more powerful, more faster per dollar. I kind of mixed my units there. But just when laptops and everything seemed like they were getting more powerful, it became very easy on an economical basis to create even more data. So, and even if you do have client server and all this fancy technology like FieldView has, the real network speed inside an organization tends to be slow, right? They'll say they have gigabit Ethernet, but what's the real throughput that someone's going to get trying to do these things? These are issues. Sharing and saving large results files takes much space and time. The interesting part about all these issues is they have nothing to do with CFD. So everybody that's focusing on CFD and all this other stuff are leaving these hard problems unsolved, which are the real bottlenecks for using CFD. So what we try to do as a company is go from this to having the engineer focus on just the important parts. So just in a nutshell, we do things to be able to, as quickly as possible, extract meaningful information on the servers from the large files. so that only a small amount of data is actually transmitted down to the person who's doing the work. So, as I said earlier, you want to spend time on the important parts of design. It doesn't do you any good to buy an HPC resource that computes more than you can use. And I can't really think of any other industry, by the way, where people do that. Like, people don't go out and buy a 18-wheeler instead of a minivan because somebody said, you need more towing power or something. It just doesn't happen in real life. But in HPC, it's easy to add more cores and more memory and increase your throughput, and then you have a problem on the other end. It's kind of an interesting situation. So we're going back to the future. We're using scripts and batch mode on HPC resources to do a lot of the work. Make the machine do the work where the data is. Don't bring the data to a small place and then try to beat on it there. Do the work where the data is located. And so in our products, we've been working for the last 5 years, batch operation. You can run, FieldView does visualization and graphics. You can run it on a server with graphic boards in the server without any heads on them, and we'll use the GPUs to do rendering by direct control rather than having to use a VNC or anything like that. We directly control these embedded rendering resources and send just the bitmaps out to the users. That's real compact, and we know how to do that since everybody streams YouTube. We know how to send bitmaps very, very well. We do parallel computing, as I mentioned. We have a kind of a unique licensing model, which I'll talk about later. We're not the typical ISV. We do not charge per core. We do not even have a licensing system for the server side of our software. If you're our customer, you're free to load that server on as many HPC resources as you want. There's no license control. What we license is the client end, the part that you sit at to do the work. So it's a reverse model. There's no tariff to embed our products in your products. So how about bike wheels? What's the Zip story? So this is a story of a project that we did. We started ourselves, then we actually started to work with the manufacturer, and then it turned out to be a missing middle story. So it was completely backwards, and I find in my life that's where I usually have the most success, is by not doing what I'm supposed to do, but doing what I think is right, and then it kind of works backwards, and then you end up looking like you're really smart. We needed applications that we could use for development. We needed to be able to run on cases with big data sets, large data, unsteady. We have a small 36-core HP cluster that we use for calculating, but customers can't give you their data. They can only tell you what their problems are, but they can't give you their data. So we needed something. We needed to be able to publish stuff that people would understand. And we needed an industrial partner who would benefit from all this. But the real deciding factor, given all that good, company goodness, is that Matt Gatto, who's the FieldView product manager, is a triathlete. And he read an ad in a biking magazine that said a company claimed that their wheels had negative drag. And that ticked him off. And so he gave me a proposal and said, hey, I want to analyze these wheels for real. And I said, wheels? We could show those, right? Yeah. And you're going to need big compute for that. Oh, yeah, it's unsteady. Yeah. Oh. So that's how this project got started. And it's been a kind of an really, really cool thing. Everybody's been benefiting. It's a rare win-win-win kind of thing. So bike wheel design. It's kind of interesting industry. It's not like your regular bicycle wheels because these things cost $3,000 a piece. $3,000 a set is the average. Some are $3,000 a piece. They used wind tunnel testing for this over the last 20 years. Zip uses a wind tunnel 3 to 4 times a year. 85 hours at $850 an hour. That's pretty expensive. If you put a cyclist in a wind tunnel on a bike, you can be measuring forces and he can find the right position and all that kind of stuff, and that's great. But if you're trying to evaluate 6 different wheel designs at 3 different speeds at 6 different yaw angles, you're going to burn up a lot of wind tunnel time. More importantly, all you get from the wind tunnel is force and moment data. You don't really see what's happening with the flow. So in a sense, wind tunnel is kind of reaching its limit today. Zip as a company is called Zip Speed Weaponry. They're the designer and producer of the world's most advanced bicycle racing wheels, if they do say so themselves. This is from their own website. But they are the only remaining U.S. manufacturer of high-performance cycling components. They have a state-of-the-art facility in Indianapolis, and they do all their design and production in one place. So if this isn't something that the U.S. should be trying to help, then I don't know what is. You know, they got a couple hundred people there. They use advanced composites to make these things. It's pretty amazing. So from Zipp's perspective, well, you know, CFD is interesting to us, but we do wind tunnel. We need stuff we can trust. And whenever we've tried CFD before, the answers don't match the wind tunnel. We can't trust it. We know that unsteady effects are really important to us, and the guys in CFD tell us, oh, that's hard. That's a hard problem. And we need these things turned around fast, very fast, because their whole product design cycle is, you know, like 18 months from an idea to shipping wheels. So they need to turn things around real fast. So that's their perspective, not knowing anything about CFD, knowing about bike wheels. Now, how many people in this room use or know about CFD? Can you raise your hand? So what happens when a CFD analyst is presented with this as a challenge? Panic. First of all, unsteady calculations are hard to set up, and they need big compute resource. They're going to result in terabytes of files. What are we going to do with those files? How do we get the unsteady turbulence models right? I mean, this is crazy, and it's coming from real geometry. It's not a stylized geometry. They want to actually take CAD and make a mesh that accurately represents it, not like knock off all the little hard parts to solve. It's like panic mode. But for people in the missing middle, they don't care about that panic. They can always build the windshield wiper and go to New Zealand and test it. They got an alternative. So Matt Gatto, being a triathlete, a guy that, I don't know what it is, you swim for like 5 miles, you ride a bike for 100, and then you run for 26. A guy like that doesn't panic, so he was ready for it. So he put together a program over the last few years. We started with an initial paper, I guess, 4 years ago for the AIAA, which is the American Association of Aerospace and Aeronautical Engineers. We've been doing this for a few years. So the latest work he did, he just presented this last week, actually. We used a large-scale HPC resource remotely. We work with Brian Kuchik and his guys at R Systems, and Dell provided us compute resource. Software and expertise from CD Adapco, and one of the things about CD Adapco as a vendor is their parallel scaling's decent, and their meshing is automatic. And as Doug Post described yesterday, meshing is usually the bane of CFD's existence, and this is an automatic meshing setup, which is very nice. And then we used FieldView in parallel and batch, and we leveraged the new data management products. So these are all this is the HPC side of coming into the bike wheel story. This is a diagram from Matt, so it's pretty complicated, but I'll just try to talk about the easy parts, for me anyway. So one case, one wheel case was 1 terabyte of unsteady data. It's not a lot, you know, in the petabyte world, but that's one case, one operating condition. So that could easily have been 18 or 24 terabytes if they were doing different wheels under different conditions. So all of this is on the remote cloud. It's all on the remote HPC resource. So essentially, these huge results never left the compute resource where they were created. Batch jobs created extract databases, which are 100 times smaller than the CFD data, 100 to 1,000 times actually with unsteady, and those were sent by FTP. We created some movies directly up there using the batch and scripting, and even some Excel spreadsheets for force and moment center of pressure calculations. So that's all done up there, wherever there is. I don't know where there was this time. That's, I guess, the beauty of the cloud, right? You don't care. Then we used FieldView servers, client-server mode, interactively to be able to display on a remote display to set up some of these batch jobs. Because that's the problem. Batch is cool, but you got to set up those jobs. How do you want to look at something? What should be the value of the Q criterion isosurface? There's a bunch of different things you have to be able to set up. But the important part is that everything stayed on the server, and everything on the HPC server was MPI parallel. So this chart is attempting to show the migration of data through the workflow. The calculation, the solver run, was run on somewhere near 64 processors. Each time step resulted on the order of 7.5 gigabytes of data. Then we start doing the reduction in FieldView. So every time step, all of the XDBs for every time step was 100 megabytes. So everything that was needed for subsequent post-processing was reduced from 7.5 gigabytes to 100 megabytes. And the important point about that is that it's lossless. And how can it be? Well, it's very simple. The CFD files contains the stuff that the CFD solver needs, like mesh topology and all kinds of crazy variables and stuff it needs for solving. But if we're doing forces, we just need the surfaces to do forces on. If we're doing isosurfaces of turbulence and turbulent intensity, we just need the isosurfaces. So that reduction is not just a blind compression. It's actually driven by the engineering requirements. And then some of these resolve forces files are on the order of kilobytes. So essentially in this data management scenario, this workflow was set up to, as quickly as possible, go to our extract databases and then subsequently post-process from the extract database, thereby reducing the time from, thousands of seconds to compute a time step, hundreds of seconds to read the real file, the whole multi-gigabyte file, down to tens of 9 seconds or 8 seconds to actually post-process the data. So when the person's sitting at his workstation, he's able to access the native data in seconds per time step. So this is an example of one of the reports that was generated for this study. This is the kind of stuff that you'd normally see at a top-end NASA or DoD kind of presentation, right? It's unsteady CFD, it's real geometry. We're looking at one velocity component here with 2 slices at different places. Here's a side view. And this is interesting. The color of the velocity is telling you whether it's going in or out of the screen. Right? So the red is coming out of the screen and the blue is going into the screen. So this was done with data that was reduced to, we created, I think, 9 cutting planes. So you could slide those cutting planes wherever you wanted with 3 functions on them for all the time steps, and it was 121 megabyte. That's laptop scale. Here's one of the big payoff pictures where you take the calculation of the unsteady results and then you average them later. Okay, so CFD is called computational fluid dynamics for a reason. It's all inherently unsteady. It's all inherently time varying. And there's 2 different ways to calculate that. The old way, which was through a formulation, kind of try to compress the time effects into a steady state picture, or the way that mostly matches a wind tunnel in an experiment, you measure over time and you average the unsteady results to get a time average on the other end. So these are time averaged pictures. So it's 5 degrees yaw versus 0. So what we've done is we've made a 0 yaw case and done the unsteady calculation, unsteady averaging, and subtracted the different yaw values, 5, 10, 15, 20, 25 degrees of yaw from the 0 base case, because that's what engineers want to look at, the difference. So if I change a design, is it getting better or worse? So we build into FieldView all these kind of automatic differencing tools. You could subtract 2 solutions from 2 completely different solvers or experimental data from CFD data and get the difference. It seems so simple, but it's just not present in tools today. So this bar, blue is a negative difference, red is a positive difference, white is no difference. So in one plot, we've got 6 different cases compared to 0 degree yaw. So what did this mean for zip? I'm going to read this because the type might be a little bit small. the Zip 808 Firecrest was the first wheel that they made using this technology, CFD technology. And Josh Portner is the main guy that's in charge of the aerodynamics and engineering and stuff at Zip. For Portner, the Intelligent Light study was a revelation. Quote, reading that paper was a huge game changer, he says emphatically. All the effects outlined in this study are ones that we could measure in the tunnel, but generally could not explain, and we definitely couldn't predict. Predictive engineering is really important. That tells you what your next step is when you're changing something. This work beautifully explains much of the why. It instantly made sense to us and recharacterized our approach to designing wheels. It made us realize we could start to design for stability, which is an important thing of riding. You don't want to fall over, I'm told. So this is a review from Tour magazine, which is a German magazine. Sensational. The fastest spoked aero wheel of all times. Aerodynamically, a revelation. Started from this ad with negative drag. It was pretty cool. So we're working with them on some more projects. We hope to be able to start something in the near future to actually now transition some of this technology to them and learn that part of the missing middle equation. The key point, as I'll talk about later, is these guys are too busy to waste time setting something up. So that's an interesting challenge to people who are interested in the missing middle. Okay, so there's some thoughts on the missing middle. I guess I'm just about at the end of my time here. So these are all images from kind of the standard high-end kind of applications for CFD and HPC, right? Aeroacoustics in the top corner, rotorcraft, that's from the AATD group at NASA Ames. The F-16 on the bottom right is from the Kestrel code, actually, is from Create, and that's from the guys at Seek Eagle in Eglin Air Force Base. This is from Neil Chatterjee. This is an actual trying to characterize the true vortex behavior of a rotor wash, downwash. And I put a logo on there from Red Bull Racing, which I don't have time to talk about. They're one of the 4 Formula One teams that are our customers. Red Bull Racing does on the order of 24 1 to 1.5 billion cell calculations every day. 7 days a week, 365. Fully automated workflow, fully automated post-processing based on FieldView. They've written scripts for FieldView that generate reports in English language that come out as PDF files that are sent all over the world. It's just amazing, their workflow at Red Bull. And the last 2 years they won. This year's going to be a little harder. But they came from nothing to winning 2 driver and constructor championships because of the strategic use of CFD. But what does this mean to the missing middle guys? So this is kind of my view. First of all, there's no budget for domain experts on staff. Domain experts are the guys that always used to take the CFD calculations with all the compromises and, well, I had to use this turbulence model, my mesh is coarse because I needed the result by Friday, all that stuff, lore, and massage it in their head and then say to their boss, well, I think this is what's going on with the flow. That's not how it works at small companies. They expect it to be just like the wind tunnel. And it's funny, at Red Bull, they do not have dedicated CFD or wind tunnel people. They have front wing people that are fully skilled in both. And they use whatever technique is best to get the job done. It's a very interesting philosophy. Engineering, not slave to the technology. The engineers there are fully committed to product development. They don't have time to take 2 guys for 2 years and learn how to use a code and validate it. It's not going to happen. 0 chance. Then the middle quote, which I think everyone's been talking about the last 2 days. Well, we think we're just fine without HPC. We're doing okay. And it isn't until, you're almost going out of business that there's like a freak out. Well, maybe HPC is going to help me. But then, of course, it's too late. Right? And they're not looking for first principles from CFD codes. Well, the CFD guys will come in, the vendors will come in and say, look, it's really good for trends. And, you can see if the air is coming in the front of this pipe, it's coming out the back of the pipe. It's good. The solution's converged. It's good. And that's very, very different from what is the uncertainty. As an engineer, I'm going to spend $500K on developing something, and you can't tell me what the uncertainty is? Forget about it. It's not going to happen. The analysis tool fidelity is just not good enough to be trusted, and that's one of the things we like about the CREATE program, is trying to directly attack that problem, and also a lot of the codes from Department of Energy. The commercial codes are meant to be easy and fast, and CFD is not either of those things. It's a very risky gamble for these guys. So from the analysis tools perspective, commercial codes are not built for scale. Everybody's been talking about that. And the real problem is most ISVs don't want to bite the bullet and recognize they have to really rewrite their code and really revalidate it and everything. It's just, for them, it's huge, a huge cost, and they're trying to ignore it. And I was at Microsoft, you know, where they talk about their new operating system. They bring in all their biggest customers. You know, for some reason I got invited there. That's when Microsoft cared about HPC for about 6 months or so. And so I got invited in there, and they're talking about Parallel and all these tools they're developing and all this and that. And the guy raises his hand from like a major business software company, billions and billions of dollars. And he goes, "My developers have told me that they don't want to even learn this Parallel stuff. They expect you to do it for us." And most ISVs have a very strange mentality, and I like to think of it because the guy in charge usually isn't very technical. That's a difference with us. You know, I came from a technical background. I kind of know you can't bullshit a bullshitter, as they say. So I could not believe that statement. This was this is one of the top 3 software companies. Amazing. FieldView is an exception. We currently scale to 128 processors per data set, and the server-side modules I mentioned earlier, they're not licensed. They're free to install, no charge. There are highly capable government codes out there, but they're not widely available, and I'm going to put that last line, they, quote, lack industrial strength, meaning that they're really not ready for the kind of user I described on the previous slide. But they'll get there. One of the things we're excited about is from the Department of Energy. They have some of the most awesome material modeling codes that there are, because they deal with strange materials over there. There's an initiative to try to find a way to bring those codes to American industry. And one of the things about those codes is they run at scale. You know, you have a code running sometimes like on something as big as the Blue Gene machine for months. So these are like machines that were in the top 10 or 20. One calculation running for months. To get a real answer, you need some real iron. And that's part of the missing middle story, I think, is not being told, which is if you're really going to be honest about the accuracy and material science, you're going to have a large-scale calculation. There's no two ways about it. So we're excited because we just received a grant from Department of Energy to take one of their data analysis backends from a product called Visit, and we're going to be commercializing that into our FieldView product to have something that scales. Today, you can run Visit on 100,000 cores for post-processing big cases. So essentially, we're taking the step, but we're lucky. We're getting funding from the government to do it. And the problem with the big ISVs, they're too big to get this kind of funding from the government. So it's probably going to be small guys that revolutionize this CAE analysis stuff over the next 10 years, not the big guys. That's my one guy's view. That's it. Thank you very much.